Hello, guys. Good morning. Good morning to all of you. Welcome to another session. Wow. Is my pen tab working? Yes, it's working. Oh, we have a loudspeaker again. I don't know in villages why people do these things. Every now and then. Big loudspeaker playing overnight. In the morning. Okay. Is everything all right? Can you hear me properly? Okay. So there will be noise, but I think most of the noise will be cancelled. We don't need to worry. We can do it. The noise is little loud, but I don't know whether it is possible for you to continue. Let me know if everything is all right. If you can continue like this, because loudspeaker has started again. If you can continue like this, because is it fine? The noise is loud, but I think most of the noise is getting cancelled because of the microphone. Is it okay, Harry? Good morning, Murli. Hearing background sound. Is it too much, or is it you can adjust? I don't know how long they will continue this background. Not rhythmic. Like when I am talking, I think the noise is not coming, isn't it? When I'm silent, maybe in that time you are getting that background sound. Okay, let's start. What do you say? Noise is coming. Oh, I have kept all my doors, windows closed, but it's still sound is coming. Clear your voice, then the sound. Yeah, you are just hearing little bit of sound, but I am I'm hearing it in full sound. It's okay. Okay, let us try. Maybe they will stop after some time, and if it is getting worse, you can let me know. We can act accordingly. Okay, so before I start, let me tell you that our BRC test series has been launched. Okay, now this time I am planning it to do in other way. Okay, it is not like I am giving you all the test in one go. I have scheduled the test, and the test is starting from today, means 10th of January 2025. So we are going firstly unit test wise. So today the test will be on mathematical methods of physics. Okay, then after 12, then some other dates are there. In this way we'll keep on giving test. Okay, MMP, CM, EMT, quantum, and so on, all the 10 units which you have, will be giving you a question, and each test will comprises of 40 questions. So that is a lot of questions. You can practice, you can give test. 1 hour is allotted, so you can try to attempt maximum marks from that, and we'll keep on doing, we will keep on giving the exams in January, then in February, and in 8th and 9th March, any day, maybe 8 March or 9 March, you will be giving your online examination, BRC online examination. Okay, so we have planned accordingly. During that course you will get 5 full length tests. Full length test means there will be 100 questions and with 3 marks each, and along with 1 negative mark. So out of 100 questions, if you can solve, let's say, around 60 to 70 questions, okay, then you will qualify. A high chance that you will qualify the online exam and you will be called for interview. And once you clear the interview, you can easily get the job. Okay, for interview also I will launch a course. I will give you the sample interview questions. I will conduct mock interviews as well, so you don't worry. For the timing, you give your main focus on the written exam. Okay, and along with that I will recommend one book by Arthur Beezer. Okay, Arthur Beezer, if you can read this book daily, maybe for an hour or half an hour, so that will be for especially for interview. This will greatly help you in cracking interviews, physics interviews. For the practice part, this test series will be sufficient, along with the GATE PIQs which we have done for GATE 2010 to maybe the recent years, whatever you get. So those will be helpful. Okay, so you can enroll for this BRC test series if you are interested in this examination. Okay, so today we will be discussing rotational spectroscopy. This is the we are starting molecular physics. Okay, this is the first part of the molecular physics, that is rotational spectroscopy. This is also called microwave spectroscopy or rotational spectroscopy, and the wavelength responsible for this rotational spectroscopy, as you can see, it is between 1 millimeter to 1 meter. Look, E is equals to hc by lambda. So you can easily get from lambda to E. If you are given E, you can find out lambda. So this equation you can use to establish a correlation between E and lambda. You see, pure rotational molecular spectra arise from the transition between the rotational energy states. Okay, now we'll see it that we'll have some energy levels, rotational energy levels. Many rotational energy levels will make a single vibrational energy level, and many vibrational energy level will make electronic energy level. Okay, so rotational energy states, rotational energy level, they are smallest with smallest interval. Okay, so rotational molecular spectra arise from the transition between rotational energy states, and that transition is observed in microwave region. The wavelength corresponding to the transition falls under microwave region, that is 1 millimeter to 1 meter in this. Okay, there is an acronym. So if you remember this, Roman man invented a very unusable X-ray gun. So from this you can arrange the different wavelengths: G for gamma, X for X-ray, U for ultraviolet, V for visible, I for infrared, M for microwave, R for radio wave. So microwave, you can see this visible region 390 nanometer to 700 nanometer, and UV, this will be less than 390 nanometer. You can see the wavelength is decreasing. In this direction, wavelength is decreasing, means energy is increasing. X-ray having more energy, gamma having more energy. Okay, and as you go along this side, your wavelength is increasing. You see, for visible light wavelength is more. Infrared, it will have wavelength more than 700 nanometer, Then comes microwave. You can see it is in millimeter. In the visible, you see it is nanometer, but in the microwave, it is of the order of millimeter to meter, and in radio wave, you know, it is in meter. Okay, hundreds of meter maybe. So only molecules that have permanent electric dipole moments can absorb or exit electromagnetic radiation in such transition. So remember the criteria, that is the molecule must have permanent electric dipole moment. It is not like it is transient, just the dipole moment creates momentarily. You will not observe rotational spectrum for them. Those molecules which have permanent electric dipole moment can absorb or exit electromagnetic radiation in this case. So for an example, HCl, you know, H plus Cl minus, so we have the plus part and minus part, and then that is separated between some distance. So this is acting like a permanent electric dipole moment, so it will show rotational spectra. In the same way, OCS, CH3F, BCl3, COH2O, these molecules will show rotational spectra. On the other hand, H2O2, N2CO2, CH4, they do not exhibit rotational spectra, so they are symmetric molecule. Okay, they don't have permanent electric dipole moment, so they will not show rotational spectra. CH4, you know, this is the structure we have read in class 12. Okay, the N2, N triple bond 2, in double bond or triple bond, I forgot. Anyways, you can see the structure. Rotational states are separated by quite small energy interval. So this is the smallest. You can see 10 to the power minus 3 electron volt. So between two vibrational level, if you consider these are vibrational level, a lot of rotational levels will be there. Okay, the absorption of rotational energy by water molecules from microwave underlies the operation of the microwave ovens. Microwave ovens operates based on this property. You can see I have shown very fine lines. So the separation, if I just show you two lines, two rotational lines, so this separation between the two rotational level is 10 to the power minus 3 electron volt. On the other hand, if I consider these are the vibrational level, these are, you can say, rotational levels. Now these are vibrational level, and many such vibrational level will fall under some electronic level, and this gap is like 10 to the power 4 times. So 0.1 means 100 times greater than the rotational energy level. You can see the difference. Okay, that is why these are rotational levels are very small, finest, and these are vibrational levels. So you can see vibrational states are separated by somewhat larger energy interval of the order of 0.1 electron volt typical. So you need to remember this order. Okay, rotational 10 to the minus 3, vibrational 0.1. Vibrational spectra are in the infrared region. You see, microwave, infrared. So lambda will be more. So you can see 750 nanometer to 1 millimeter. And next 1 millimeter to 1 meter, that is the microwave, and this is infrared. So vibrational spectroscopy, that we will discuss in the next class. Vibrational spectroscopy is also known as infrared spectroscopy, because the transition between the vibrational level corresponds to infrared region. Okay, that is why this is also called infrared spectroscopy. And since the transition between the rotational level falls in the microwave region, it is called microwave spectroscopy. Molecular electronic state, it is larger than the vibrational energy. So you can imagine it in this way. Let's say these are rotational one, and let's say these are vibrational one, and here in between we have electronic. Okay, the smallest rotational, larger than them vibrational, and many vibrational is making electronic. So this simple thing you need to understand. Molecular electronic state have the highest energy with typical separation between the energy level of outer electron several electron volt. Like you can consider the case of hydrogen atom. In case of hydrogen atom, the outermost electron is having the energy minus 13.6 by n square. This is the, so it is in electron volt, right? So by putting different values of n, we get energy in several electron volts. So the transition will form the electronic states. Okay. The corresponding spectra are in the visible 390 nanometer to 750 nanometer. So you see, microwave, rotational spectroscopy, infrared, vibrational spectroscopy, then visible. Okay, this is electronic. So if you are going along this line, what is increasing? Your lambda value is decreasing, means energy is increasing, right? If you are going along this, your energy is increasing. Is it getting clear? Visible, or it can also go to ultraviolet region 10 nanometer to 400 nanometer. This spectroscopic range, wavelength, in terms of wavelength, you should remember. Okay, so for a short trick, you can remember this line: Roman man invented a very unusual X-ray gun. So you should also remember the wavelength, corresponding wavelength. I will share, I have a good note on this. I may share, you can just remember me in the group or DM, I will share if I forget. Electric dipole moment is generated where there is a separation of charges, positive and negative. You can see delta plus, delta minus. So this is carbon monoxide, so it has a permanent electric dipole moment. And so CO shows rotational spectroscopy because there is a separation between the positive and negative charge, and it shows rotational spectroscopy. So I hope you have got pretty much idea about the rotational spectroscopy. For theory part, we have few things more. This is a basic thing. So you understood what is rotational spectroscopy and in which region it works. Let's take a problem, simple problem. I think you can do it with your own knowledge. If you have the knowledge of spectroscopy, spectral region, you can do it. Match the typical spectroscopic regions specified in group 1 with the corresponding type of transition in group 2. Can you do it? Tell me the answer quickly. I think you can do it. See? Yes. So you see, infrared region means vibrational transition of molecules, you know, vibrational spectra. UV region corresponds to visible UV electronic transitions involving valence electrons. X-ray, you know, transition involving inner shell electrons. We have already started this. Gamma related to nuclear transitions. So it is matching with option C. Okay, very simple. So you see, it is not necessary that you need to know everything in such questions, and from atomic this type of questions is set sometimes. Okay, so if you know 2-3 of them, you can easily attempt the question. And here in this case, you can see that if you only know one option, then if you know P3, if you know this correctly, then the other will follow, because there is no other P3. So weak level of questions. So that thing is written here. चलो आगे बढ़ते हैं. So let us try to understand the rotation of molecule. Okay, the rotation of molecules. Obviously, rotational spectroscopy related to the rotation of the molecules. Now, how different molecules rotate, we need to have little bit of idea about that. Firstly, we will consider linear molecules. So, some molecules which has linear structure. So, what are the examples of linear molecules? Can you give me an example? Can you give me some example of linear molecule? Anyone? Just give me some example of linear molecule. Okay, maybe it's wrong, but you should try to answer. Okay, what do you think? Any molecule you know which is linear molecule? Carbon monoxide, very good. Carbon monoxide, HCl, ठीक है, HCl, carbon monoxide, and you are right, CO2 and OCS, C2H2, C2H2, ethylene, CH. Now, I am taking a particular case of one linear molecule, HCl, let's say. So, if you consider that H and this is Cl, just this is for representational purpose. Let's say this is H, this is Cl. So, in this way, the molecule is made up of, you can say, this is how the molecule is. It's a linear molecule. So, linear means this HCl. Okay, now if we consider three axes, let's say one axis may be like this, another axis may be like this, and this is one axis usually. Now, if you calculate moment of inertia about axis, so moment of inertia of this molecule about this axis, if you calculate, let's say that is IB. You can also calculate, it is like you have this linear molecule, okay? You can rotate it in this way. In this way, if you can rotate, can you see it? In this way, you can rotate. So, you are rotating, let's say about the Z axis. So, this is this, in this way you can rotate. So, you can get moment of inertia about the axis perpendicular to it, and you can also rotate in this way, right? In this way, in this way. So, you are rotating about this axis. So, you will also get moment of inertia. So, let's say that moment of inertia is IC. So, three axes we have, maybe X, Y and Z. So, along this, about this axis, the moment of inertia is IC. About this axis, moment of inertia is IB. So, you can imagine it in this way. About this axis, it is IB. About this axis, it is IC. Now, about this axis, what will be the moment of inertia? IA. So, what should be the value of IA? Forget about IB and IC, they are non-zero. IA will be how much? 0, right? Because you can see the line joining is this. So, if you rotate about this, will you get any moment of inertia? It is rotating about its own axis, right? So, you will not get any moment of inertia for this case. 0, IA will be 0. And it is found that for this kind of linear molecule, the value of IB and IC are same, and value of IA will be 0. Okay, I hope this one is understood. So, this is the first type of molecules, linear molecules. Next, another type of molecule exists, symmetric tops. Symmetric tops. So from the name itself, you can make a guess. Symmetric tops. So these molecules are symmetric. CH3, Cl. Let's say NH3. These are not linear. Okay. BCl3, CH3, Cn, CH3, F. So if I give you one example, let's say CH3F. So carbon, the valency of carbon is 4. Okay. So 3 hydrogen is connected like this. So another vacancy means another bond, F. So this is a symmetric top. Okay. Let's say for this case, you can say for CH3F, this is the structure. For this case, you can say IB is equals to IC, which is not equals to IA, and IA not equals to 0. The actual structure of the molecule, we have to see it from the chemistry. It is not like HCF are in one line. Okay, there may be some angle. So this is observed. The IB equals to IC not equals to IA, and IA not equals to 0. Okay. If I take the case of BCl3, let's say BCl3. So it has a structure something like this. Chlorine is connected with boron in this way. So for this case, it is observed that IA is equals to 2 times IB, which is equals to 2 times IC. Okay, this is observed. So you don't need to worry about this. We'll solve some problem, there we will understand what kind of thing it is referring to. So these are the examples of symmetric tops. Another one, asymmetric tops. Third one, asymmetric tops. Asymmetric tops. For asymmetric tops, we have, let's say, H2O, H2CO, CH3OH, CH2, CH2. Like hydrogen, okay, oxygen, hydrogen. This is water, and here it is observed IA not is equals to IB, not is equals to IC. So various kind of structure is involved. This is CH2, CH2. Okay, in this way. Fourth one, spherical tops. Spherical tops. So you can easily understand what kind of molecule will fall under this. Molecule like CH4, methane, SiH4, this is symmetric, SF6, CH4. So for this kind of molecules, you will remember IA is equals to IB is equals to IC. Okay, for symmetric tops. Whatever be the direction, you will get the same moment of inertia value. This CH4 is not rotational active. Molecule, because it does not have permanent dipole moment. It does not have, it's not about permanent, it doesn't have dipole moment. It doesn't even produce transient dipole moment too. Okay, now let us talk about this moment of inertia thing in more detail. We'll try to take a diatomic molecule and we'll try to find out the moment of inertia expression. Okay, so rotational spectra of diatomic rigid rotator. So we have a rigid rotator. Okay, so this rigid rotator consisting of two atoms. Okay, so this molecule is consisted of two atoms. One is M1, another one is M2. Okay, so M1 is rotating in this way, and M2 is rotating in this way. Let's say this is the path of M2. Okay, and maybe this is the center of mass. So along the center of mass we are drawing a line, and let's connect the center to center of these two molecules. So this intersection gives you the moment of inertia, center of mass. This point refers to the center of mass of this molecule, and the distance of the mass M1 from the center of mass is, let's say, R1, and the distance of the mass M2 from the center of mass is R2, and the total separation, let's say, we are calling it capital R. Okay, this is the case. So you see, the moment of inertia of the system about the axis of rotation perpendicular to internuclear axis and passing through the center of mass. So this is talking about this rotation. Okay, so about this axis, what is the moment of inertia? So you know the formula, I is equals to sum over mi ri square. Okay, sum over all the masses. So here two masses we have, mass M1, so M1 R1 square plus M2 R2 square. Now you know the definition of center of mass. Okay, so from the definition of the center of mass, what you can write? From the definition of center of mass, we can write, what you can write? You can write that M1 R1 should be equals to M2 R2. This is how the center of mass is obtained, isn't it? This definition we can have from the center of mass. M1 R1 is equals to M2 R2. Now if you just find out one value of, let's say you are finding out the value of M1 and put it here, you will end up getting this value, I is equals to M1 M2 by m1 plus m2 multiplied by r1 plus r2 square. This term is identified as written as mu, and r1 plus r2 is capital R, so it becomes mu r square, where this mu is the reduced mass, of the diatomic molecule. Okay, mu is equals to m1 m2 by m1 plus m2. So you need to remember this one. Okay, mu is equals to m1 m2 by m1 plus m2. This is the reduced mass. Now I am giving you this as homework, like how from the definition of center of mass, by putting, let's say, by writing m1 is equals to r1 is equals to m2 by m1 into r2, you can put it in the expression of I and you can obtain this. So try to obtain this expression. I'm leaving it for homework. If it is not solved, you can let me know, I will provide you the solution. Okay. Sorry. So you get the moment of inertia I is equals to mu into r square. Now this is the diatomic molecule. Now this will rotate, and because of this rotation you will get rotational energy levels. Okay. Now for this, the allowed energy levels of this rigid diatomic molecule is, we are denoting it by Ej. So for rotation, you know the energy value. What is that? Half I omega square. We have read it. So this can be written as L square upon 2I. L equals to I omega. L is the angular momentum. And from quantum mechanics, you know the value of L square. L square, you know, root over, okay, root over is gone because it is L square, L into L plus 1 h cut square. You can also express it by J into J plus 1 h cut square. So sometimes L is represented by J. It is not, it is like angular momentum. Okay, J is angular momentum, same thing. So L square by 2I, so we can write it as h cut square upon 2I J into J plus 1. So what is this J? J will be denoting as rotational quantum number. Rotational quantum number. Okay. So this is the energy level. Now if you know, in atomic molecular physics, things are represented in terms of wave number. So if you want to express this in terms of the wave number, we can write Carly Ej, and you know it very well. How to get the wave number? You need to divide the energy value by Hc. We have also done it in case of in the chapter of Zeeman effect, we have seen. So divided by Hc. So if you divide by Hc, what you get? H cut square by 2I, it is meaning h square by 8 pi square I. So one h is gone, so you will get h cut divided by 4 pi I c. You can imagine it in this way: one h cut you keep, another h cut is h by 2 pi. So h get cancelled, 2 pi is multiplied, so 2 pi into 2I, so 4 pi I and this c. Okay, J into J plus 1, and h cut by 4 pi IC, this is called B times J into j plus 1, where this j can take values 0, 1, 2, 3 and so on. These are called rotational quantum number. Okay, so in terms of B, if we write Ej can take these values. If you put j equals to 0, you get 0. If you put j equals to 1, 2b, 6b, 12b and so on. Okay. B is equals to h cut by 4 pi IC. This is, if you write in terms of h by 8 pi square IC. Can I write it? Now, if we consider a transition, for a transition from j prime to j double prime. Remember every time that whenever we have j double prime, that is 1 unit lower than the prime. So note that j prime is j double prime plus 1. So j double prime is the lower one. Okay, these are simple thing but very important for conceptual purpose. J double prime plus 1. So you can imagine it in this way. This is j double prime level and this is j prime level. Okay. So for this the energy is E j prime, for this the energy is E j double prime. So if we have some transition here, okay, so what will be the corresponding wave number, nu bar? We can write it E j prime minus E j double prime. This is equals to B j prime plus 1 minus B j double prime plus 1. Okay. Now if I put the value of j prime is equals to j double prime plus 1, then what you can write? This can be written as B j double prime plus 1 into j double prime plus 2 minus B j double prime times j double prime plus 1. So you see what value will you get? B j double prime plus 1 into j prime, that is cancelled. What you have? 2b times j double prime plus 1 you will get. So we are getting nu prime is equals to 2b times j double prime plus 1. So it means it has got the values. If you put j double prime is equals to 0, you get 2b. Okay, 2b, j prime is equals to 1 for b, j double prime is equals to 2, 6b, 8b and so on. So you can see there is a gap of 2b. Thus the absorption spectrum of a rigid rotator is expected to consist of a series of equidistance line with constant separation to be. Just a moment, I am getting a call. Hello? Yes, ma'am. Good morning. मैंने चेक नहीं किया. ठीक है, ठीक है, ठीक है. अभी तो आज की छुट्टी है हमारी. हाँ, कल तक तो भूल जाना चाहिए. आज से छुट्टी हो गई, आज छुट्टी है. हम्म, हाँ हाँ हाँ. तो बैंक छुट्टी रहेगी, बैंक छुट्टी नहीं रहेगी. लास्ट बार भी तो बुधवार ही पड़ा था. टीचिंग वाले हैं, उनसे टाइम पर. देखता हूँ, कोई अपडेट मिलेगा तो आपको बताऊँ. ठीक है, ठीक है. Okay, you see, your main focus will be on this line. This is giving you the energy for each rotational energy levels. Ej is equals to 0, 2b, 6b, 12b. So if I okay, I don't have space here. Anyways, if you consider this 0, 2b, double the, it is like it is getting doubled. You can see 0, 2b, 6b, then 12b somewhere here, and so on. Okay, it is like that. These are the value of Ej: 0, 2b, 6b, 0, 2b, 6b. So every time it is getting double, not 12b. Next will be 20b, not double exactly. 4, if you put 4 into 5, 20. Huh. So you can see the gap. This is this gap, absorption, this gap. What are these values? These are the values of Ej. Remember. Okay. By mistake this line came. Anyways, now the absorption, you can see this to this, the gap is 2b. Rotation means absorption, although we have done the calculation for emission type, but the gap is same, na? Whether it is coming from this to this or it is going from this to this, the gap is same. You see, this gap is constantly increasing. And what is this value? That value is, you see here. Here you can see the absorption from between the first two level, it is 2b. Between these two level, it is 4b. Difference gap 6b, and this is 8b. Understood? And you can imagine that this is the J values. These are the J values 0, 1, 2, 3, 4, and it will go indefinitely. Okay. And you see the transition in this way. You will get a line for 2b. Next, you will get 4b, 6b, 8b, 10b, and so on. Okay. So you see, this is 2b, 4b, 6b, 8b, 10b. This is the spectrum. This is in centimeter inverse you will get. These are the value of nu bar. Nu bar you calculate in terms of centimeter inverse. Okay, now for an example, what are we doing? Let's say this constant separation of, so the absorption spectrum of a rigid rotator is expected to consist of a series of equidistant lines with constant separation of 2b. So you can easily see it between these two lines, separation is 2b, between these two lines, separation is 2b, here 2b, here 2b. All these separations are 2b. Okay, if I let's say calculate now to verify this, that the separation is 2b mathematically, nu bar, let's say I'm writing a small j is equals to 0 to j equals to 1. You can also write in terms of capital J, same thing, j equals to 0 to j equals to 1 in this level. So the difference we want to know, so j equals to 1 is higher energy level. So j equals to 1, we are calculating in terms of the wave number, that is why we are writing curly e, not the capital E, minus E j equals to 0. Okay, j equals to 1, the level is 2b minus 0, that is 2b, and the unit is centimeter inverse wave number. Let's say nu bar, we are considering the absorption of j equals to 1 to j equals to 2, this level. So this will be E at j equals to 2 minus E j equals to 1. 6b minus how much? 6b. Have we done any mistake? Minus 2b is equals to 4b centimeter. That is what we have got. But the gap is 2b. Now, most important thing here, the selection rules. Selection rules for rotational spectrum. What is the selection rule? You know it. Selection rule for rotational spectrum, delta J is equals to, you see, every time I have shown the transition between the nearby levels from this to this, or this to this, or this to this. I have not shown any transition from this to this or this to this. So delta J is equals to plus minus 1, that is the selection rule. There is no 0, okay, only plus minus 1. So it can go from 1 to 2 or it can come down from 2 to 1. So the rotational, it is basically absorption, right? Infrared, microwave, so you will get absorption. So it will go from 0 to 1 or 1 to 2 or 2 to 3 this way. So I hope the theory of this rotational spectroscopy is done. Anyone has any doubt, you can ask now. This much theory is sufficient to tackle problem in your examination. Murli, Karthik, Harry, Ajay, tell me if you have any question. चलिए एक प्रॉब्लम करते हैं. Let's try this problem. Consider the hydrogen deuterium molecule as T. Hydrogen deuterium molecule, this is the diatomic molecule. If the mean distance between the two atoms is 0.08 nanometer, R value is given. Mass of the hydrogen atom is given. So mass of deuterium you can easily calculate, 1H1, this is 1H2. So 2 times the mass of hydrogen. Energy difference delta E between the two lowest rotational state. So you can easily calculate, I think. Give it a try. Simple question. Are you able to solve it? Look, what do you know? E is equals to h cut square by 2i j into j plus 1, this one you know. So if I write it, h square by 8 pi square I j into j plus 1. So let's call it a, some constant a times j into j plus 1. Can I write it? Where a is equals to h square by 8 pi square I. So you have to find out delta E between the lowest two rotational energy levels. So one will be j equals to 0, another will be j equals to 1, j equals to 0, j equals to 1. If this is A with j equals to 0, this will be 0. With j equals to 1, 1 plus 1, so this is 2a. So this gap you need to find out, so that gap is 2a. Okay, so the difference between two lowest energy levels is delta E is equals to 2a. Now if you can calculate, you are dealing only with absorption case, but yes. In the selection rule, delta J equals to plus minus 1 is given, but mainly in rotational spectroscopy absorption is happening. Okay, it just so that only the nearby transitions are allowed. It can go from 1 to 2, or it can come down from 2 to 1. Okay, if I take this delta J equals to plus 1 to be absorption, minus 1 is related to emission. Yes, you are right. You can imagine it in this way, that you are using microwave and you have given energy, and let's say it has reached to this J equals to 3 level. So if it wants to come down to J equals to 2, it can come. So 3 to 2 it can come. Okay, it cannot come directly from 3 to 1. So we need to calculate this value of 2a. So firstly let's calculate a. A depends on the value of I. Okay, a h square by 8 pi square I, and I is mu r square. What is mu here? It is a system of hydrogen and deuterium, and the internuclear distance, let's say, that is r. Okay, so mu is equals to mass m1 m2 by m1 plus m2, mass of hydrogen, mass of deuterium divided by mass of hydrogen plus mass of deuterium. So mass of hydrogen and mass of deuterium is 2 times the mass of hydrogen. You know it already. Mass of hydrogen plus 2 times mass of hydrogen. So this is nothing but 2/3 mass of hydrogen. Now mass of hydrogen is given to 938 MeV per c square. So we can just put the value of mass of hydrogen 938 MeV per c square, and that can give you some value. Okay. Now if you just put this value in the given expression, you can get it in terms of A. A is equals to h square by 8 pi square I, or you can also write it h cut square by I actually. H cut square by 2I. H cut square by 2I delta E, that is 2A. So 2 into h cut square by 2I, or h square by 8 pi square I, whatever you write. Ultimately you are getting h cut square by I. So h cut, you know the value of h cut. H cut, if I calculate separately, h cut is equals to h by 2 pi. This has the value 1.01 into 10 to the power minus 34 joule second. Okay, so if you want to express in terms of electron volt, we have to divide it by the mass of the electron, 1.6 10 to the power minus 19. You will get it in terms of electron volt second, and this will give you the value of 6.3 into 10 to the power minus 16 electron volt second, because the value of I we have got in terms of mega electron volt per c square. So we have to write the value of h in terms of electron volt if you want to just put this value in. So 6.3 3 into 10 to the power minus 16 electron volt second square. Okay, you are getting divided by 2 by 3 into 938 MeV. MeV means 10 to the power 6 eV. So we have written in terms of eV. Okay. If everything is written, there is mu r square. R value is given to in the question. R is 0.08 nanometer. So let's put it in SI unit, 0.08 nanometer. Okay, 0.08 nanometer. So 0.08 10 to the power minus 9 square. Okay, and this will give you approximately 9.2 10 to the power minus 3 electron volt. So this is approximately 10. So 10 to the power minus 2 electron volt. Option B. Clear, Murli, Karthik? Karthik, are you not appearing for BRC exam? I'll recommend everybody to appear for BRC exam, because if you want a job, at very good job actually, under the age of 27 or 26, whatever it is, you should definitely try this. Great opportunity every year you get, and main hurdle is qualifying the interview. If you are good at physics, you can easily crack the written, but cracking the interview is a little bit difficult. But if you make your concepts clear, then you can do it. Okay, let's do it. The three principal moments of inertia of a methanol molecule have the property this: the rotational energy eigenvalues are. Okay, can you do it? This requires the knowledge of quantum mechanics. Simple question, but you need to have the knowledge of quantum mechanics, and as far as this question is concerned, you can solve it based on whatever we have discussed. Yes, because here only the eigenvalues of jx square, sorry, jz square and j square is required. That is a hint. Can you do it? So this is an example of symmetric top, right? Ix equals to ii, equals to I, Iz not equals to I. So I think this is the example of, yes, symmetric tops. Look, this question is very simple. Rotational energy eigenvalues you need to calculate. You know the value of the rotational energy. What is that value? Half I omega square. Now, let's start from the grass. So this is L square by 2I. Okay. Or L we can write in terms of J as well. J square by 2I, because in rotational quantum number J is used. So J square can we not write as sum of Jx square, Ay square, Jz square, because different dimensions are involved. So we are writing J square as the sum of Jx square, Jy square and Zz square. Now corresponding to different axes we will have different I values. Okay. If you are rotating about x axis you get the moment of inertia Ix. If you are rotating about y axis you get Iy, and if you are rotating it about z axis you get Iz. Therefore we can write this energy expression is equals to, you see, Ix Iy is equals to I, J square by 2I. So I am just writing is in this way. So for simplification, Jx square by 2I, okay, let's say x, plus Jy square by 2Iy plus Jz square by 2Iz. So we can write it 1 upon 2I Jx square plus Jy square plus 1 upon 2I Z Jz. Can I write it? Now from this you can see that Jx square plus Jy square is nothing but J square minus Zz square, and thus we can write E is equals to J square by 2I by putting this minus Jz square. So plus 1 upon 2 Iz minus 1 upon 2I Jz square. Can I write it? Now you know the quantum, this is a classical expression. Okay, this is the classical expression, of energy. Now quantum mechanically, you know, things are quantized. Quantum mechanically you know the values of J square. Quantum mechanically what will you write? J square is h cut square into J plus 1. Okay, quantum mechanically. And Jz, you know, Jz equals to m h cut. So mj h cut, square, Jz square, so h cut square mj square, and this 2 is taken common, 1 upon Iz minus 1 upon I, which is matching with option C. Clear? It is matching with C or something else? Not C, it is actually matching with A. The last step, which one? This one. You know the quantum mechanically J is equals to root over J into J plus 1 h cut. If you want to match it with the answer, it is like root over L into L plus 1 h cut. Okay, and Jz is equals to M J h cut. These two relations we know. So just put the value J square root over is gone, J into J plus 1 h cut square, and Jz is square. So Mj square h cut square. This 2 is taken common, 1 by Ij minus 1 by I. Now clear? Harry, Murli, Karthik, Ajay. Let's go to the next problem. The rotational spectra of rigid diatomic molecule contain spectral lines separated by 0.6 centimeter inverse. Moment of inertia of the molecule is. Okay. What is given? The rotational spectra of rigid molecules contain spectral lines separated by a distance of 0.6 centimeter inverse. So this difference is given to you as 0.6 centimeter inverse. You already know what is this value. This is 2b, right? So from this value of 2b you can easily calculate moment of inertia. Tell me the value quickly. So what is given? 2b is equals to 0.6 centimeter inverse. Right. What is b? B is equals to h cut by 4 pi IC, that is how much? H by 8 pi square IC. And therefore 2b means 2 into h by 8 pi square IC is equals to 0.6. So what is I? H by 4 pi square C into 0.6. Value of H 6.626 10 to the power minus 34 divided by pi square 3.14 square, speed of light 3 into 10 to the power 8 and 0.6. Now you see 0.6 centimeter inverse. So if you want to get it in SI, so 0.6 centimeter inverse, it means 0.6 by 1 centimeter. 0.6 by 1 centimeter is equals to 10 to the power minus 2 meter, you can say. 100 centimeter is equals to 1 meter, so 10 to the minus 2 meter. So it is like 0.6 into 10 to the power 2 meter inverse. Okay. if you want to, if you are expressing everything is in SI, so you have to write 0.6 into 10 to the power 2, right? Here also 0.6 into 10 to the power 2. So you can just multiply 10 to the minus 2 here. Okay. We are taking it to the numerator. Here you can write 10 to the minus 2. Then this, what will be the unit? Kg meter square. So you have to take care of the units, proper units. So 0.6 centimeter inverse, some centimeter inverse in this process you can easily calculate in SI unit meter inverse. And if you calculate, this value will give you 9.3 10 to the power minus 46 kg meter square. Option C. Tell me guys if you have any question from this question. Okay, if there is no question, let's start another topic, the intensities of the spectral lines. Okay, the factors deciding the intensity of the spectral lines are: the first factor, number of molecules in each level, number of molecules in each level. So how do you decide that? It is decided by Maxwell-Boltzmann distribution, MB distribution. Okay, Nj by N0, this is exponential minus Ej by Kt, this is equals to exponential Ej, you know the value, Hc times B into J plus 1 by Kt. Okay. Can I write it? What was that? Ej was Ej by Hc, and that was equals to Bj J plus 1, right? So from this, Ej is equals to Hc times Bj J plus 1. That is why we have written it. I hope this is understood. So, this is the first factor, that number of molecules present in each level, and the second factor is degeneracy. Degeneracy in the energy level. That is existence of two or more states with exactly the same energy. That is the concept of degeneracy. If you consider one J level, so each J level has how many degenerate level? Each J level has 2J plus 1 fold degeneracy. Degeneracy is expressed in this term, fold. Two-fold means degeneracy is 2, 3-fold, 4-fold, 5-fold, 7-fold, and so on. So, if you consider the total relative population, population means you can see the number of molecules present in that level. So, the total relative population, at, let's say, energy EJ is, so it is combined effect of both A and B. Okay, so it will be population in the level of EJ is proportional to the degeneracy factor 2J plus 1 into the Boltzmann factor minus EJ by 80. Don't include Maxwell, it is decided by Boltzmann distribution. So, this is the population of a particular level with energy EJ. What is the maximum population? Maximum population formula. Maximum population is given by corresponding to, so which J level is corresponding to the maximum population. So, that is J max. For the value of J for which the population will be maximum is given by root over KT by 2H CB minus half. You can easily prove it by taking the derivative with respect to J and finding the derivative equals to 0, setting the derivative d population by dj equals to 0, you will get the value of J. Okay. So, this is the maximum population formula. So, it is more like you can represent it graphically. If you want to see it graphically, it is like this. If you are representing the relative population, let's say a relative population along the y-axis, and you are putting the value of J along the x-axis. So, you can have a graph like this. So, this value corresponds to the maximum population, maybe, yes, J max. This is the maximum population predicate. Now, this J max may be varied if you consider different isotopes. So, let us try to understand that. Effect of isotopes on the rotational spectrum. Effect of isotopic mass on rotational spectrum. So, how will you deal with it? So when a particular molecule, when a particular molecule, okay, so particular atom in a molecule, particular atom in a molecule is replaced by their maybe an isotope, is replaced by its isotope, then obviously I value will be changed, changes in total mass, because mass of the isotopes are different, right? Changes in total mass, in the moment of inertia value, that depends on mass, or the B value, rotational constant, or B value take place. If those things are changed, the spectrum will be changed. If I take an example, let's say we are considering carbon monoxide. Okay, carbon monoxide, it is consisting, we can make it by taking the C12 and 16O. This is carbon monoxide. So for this, let's say we are getting the reduced mass, maybe mu. If I take the another isotope of carbon, let's say 13C, and keeping 16O fixed, so we have just changed a particular atom in a molecule. So masses are changed, so you will get different reduced mass. Now the formula is M1 M2 by M1 plus M2 for this isotopes, for the moment of inertia. Now mu prime is found to be greater than mu, that is the reduced mass of the isotopic molecule will be greater than the reduced mass of the actual molecule. Okay, this was the actual molecule 12C16O, but the reduced mass is slightly less than that of the actual molecule. And because of that, if you plot the relative population, you will get different curves, because B value is also changing. B value depends on, you see how B is deciding factors. B is the deciding factor. You know, B h cut by 4 pi IC, B is depending on I is depending on mu. In this way, if mu changes, I changes, and I changes, B changes. And that is why if you plot the relative population for these two molecules, what you will get? Depending on the value of the B relative population, so we are plotting along the y-axis and J along the x-axis. So let's say for B is equals to 10 centimeter inverse, if you get a curve like this, let's say this is for B is equals to 10 centimeter inverse, we can get a different curve like this for B is equals to 5 centimeter inverse. Okay. You can say that J max value is reciprocal, is proportional to, if you Just ignore this minus half factor. You can see it is proportional to 1 upon square root of b. So more the b, less the maximum value. You can see that is why it is shifting towards right for higher value of b. Things are getting clear, guys. One last formula I would like to give you here. Rotational partition function. We should have given it in the canonical ensemble chapter, but for the timing you just note it down. Rotational partition function. Rotational partition function, it is given by this formula of ZR AT by HCP. Okay. Let's solve another last problem. This is the last problem for today's session. The first spectrum, absorption spectrum of 12C16O is at 3.842 centimeter inverse, while that of 13C16O is at 3.673 centimeter inverse. Ratio of their moments of inertia each. Okay. So it is, if you represent it, what can you say? Let's say this is for 12C16O, right? And for 13C16O, like this. You can imagine it in this way. This is for 12C16O, and this is for 13C16O. So from this you have to calculate the ratio of their moment of inertia. First absorption value, where do you get it? At B1, at B values, right? So let's call this is as B1, this is at B2. Actually 2B1, right? First line you get at the value of 2B, then 4B, then 6B and 8B. Option C, very good, option C. So let's say if you are calculating for 12C16O, okay, 12C16O, let's call it 2B1. This is the location of 2B1, 3.842 centimeter inverse. On the other hand, for 13C16O, again 2B2, B values are changing. This is 3.673 centimeter inverse. So what is the value of this B? B, you know, H by 8 pi square I C. So we can write B1 by B2 is equals to, it is reciprocal of I and other things are constant, so I2 by I1. So ratio of the moment of inertia you have to calculate. So if I want to calculate I1 by I2, okay, then it will be B2 by B1. So what are you getting? Look, we should calculate I2 by I1. I2 by I1, right? I1 will be less because B is proportional to I. So if you have larger B, I will be less. So you have to we should calculate I2 by I1. That will give you positive result. Okay, means positive means more than 1. Okay. Are you getting what I am trying to say? So you see, the options are given more than 1. It means the moment of inertia you have to calculate. If you write I2 first, then I1, because you see B is proportional to I. So if B is less, I will be more. Okay. So B is less for which case? B2. So that is why we are calculating I2 by I1 to get more than 1. Okay. This one I hope you have understood. B1 by B2. So 3.842 by 3.673. So approximately 1.046. If anyone has any question, you can ask. So with this we complete the rotational spectroscopy. In the next day we will complete vibrational spectroscopy or maybe electronic spectroscopy as well. Then after that we will go for Raman effect. These topics are easy topic and important topic. If you get one question, you can these are like bonus. If you get a question, you will be able to solve in few steps and you can easily get 5 marks. Question of 5 marks will come. Okay. With this, let me end the session, and guys, those who are appearing for BRC exam, you can join the test series. The first test is starting today from 3 p.m. You know, your exam may be on Saturday and Sunday, the real exam, and it is generally taken in the afternoon session, maybe from 2 p.m. or 3 p.m. So that is why all the tests will be taken from 3 p.m. Okay. So just keep on practicing questions. Don't run too much for the theory. Okay, theory you have sufficiently done. If you cover the top 100 topics, the theory part is done. Now it's your job to solve as many questions as possible. I am providing you test series. We have a NET test series, lot of questions are there. We have GET test series, lot of questions are there. Now I am introducing the BRC test series. So you can imagine how different numbers of questions you are getting, and the questions are different. It's not like same questions I'm giving. Only the Sunday test questions are same. So if you just keep on practicing questions, then that will be helping you to strengthen your numerical ability, and that is required whether you want to crack JRF or want to crack GATE or BRC. Numerical ability is one thing. That thing is necessary. In your BRC interview also, you will be asked to solve some numerical questions as well. Okay, to strengthen it. Bye bye. Let's end the session here, guys. Thank you. See you in the next class.